Okay, so let's start with convergence in probability. Several questions. Okay, so here's the first one. Now, suppose you have a sequence of random variables. When you have xn, that means it's a sequence of random variables. Okay, all of them are exponential with the parameter n. You have to show that xn goes to 0 in probability. So when you see a question like that, what are the information you know? So your xn is the sequence of random variables. All of them follow exponential distribution with parameter n. So that means you can write the density of x, which is n e to the negative n x, x greater than 0, 0 otherwise. Now in examinations, we provide the PDFs of whatever the distributions we will be need in the examination. So you may have seen that in most of the ST201 exam papers, at the end of the last question, you will see a small table with some probability distributions. They are PDFs, and sometimes the moment generating function also. Okay, so those things will be available for you. So there's no need to memorize the PDF of the exponential density or whatever the distribution that will be given. Sometimes the effects will be given in the question itself. If not, it will be available as a supplementary information. Okay. So you know that this xn follows the exponential with parameter n. Okay. Now you know sometimes you usually use the parameter theta, lambda, and so on, but in this case, this is n. You want to show that this series converge in probability to 0. So when you see this convergence in probability to 0, okay, the thing that you have to do is, this is what we have to show. When we do questions, you will see that this is the same thing actually. Okay? What you have to show is, we have to show that the limit when n goes to infinity, probability, this xn minus this 0 that you see where it converge greater than or equal to epsilon equal to 0. This is for some epsilon greater than 0. Okay, so this is what you have to show at the end. The limit n goes to infinity, the probability of this absolute value xn minus 0. Xn is the value you see in your convergence, and 0 is where it should converge. So xn minus 0, the absolute value greater than or equal to epsilon, it should be 0. So somehow we have to show that our right hand side goes to 0. Okay, right, we'll try to do that. Okay, so I'm going to write the left hand side again. So that's a question. Do you have to familiar with the gamma distribution? If there is a question with the gamma distribution, the PDF will be given to you. Okay, and if you need the variance and the expected value, those things will also be given to you. So you do not have to memorize it. Okay. Right. So here's my left hand side. Right, but since this is 0, you can write this as simply the probability is xn is greater than or equal to epsilon. Okay. Now, why are we omitting the absolute value? Why are we omitting the absolute value? Because we know xn is exponential, and always the exponential random variables are greater than 0. That you should know. Okay, the support of this, the distributions. The normal distribution, x can contain any value from negative infinity up to positive infinity. If you think about the exponential distribution, always the x will be greater than 0, only the positive values. There are no negative values possible for exponential random variables. Therefore, you can omit this absolute value sign also. So you can simply write xn greater than or equal to 0. Why? Because xn is exponential. Okay. And all xn's, all xi's are greater than 0. Therefore, you can omit the absolute value, right? Okay, so what is this? What is this probability? Xn greater than or equal to some value. Now epsilon is some number, okay, some small number. Now, if you look at this probability, this is the complement of the CDF, right? This is the complement of the CDF. Why are we saying it is the complement of the CDF? How do you write the CDF? CDF is capital Fx. The definition of the CDF is probability x less than or equal to x. Now, if you have the complement of this, that is 1 minus Fx, that will be probability x greater than or equal to x. When x is continuous, the equal sign does not matter. So this is the complement of the CDF. So if you can find the CDF of this exponential density, you can easily find this the right hand side. Okay, so let's start finding the CDF of the this exponential density function, right? So we already know Fx is n e to the negative nx, x greater than 0, 0 otherwise. We have to find the CDF of x. How do you do that? You have to integrate Fx from where to where? The lower limit up to any x. Okay, the lower limit is 0 for exponential. X is greater than 0. The lower limit is 0 up to any x. So let's do that. Integrate from 0 to x, n times e to the negative nx dx. Okay, you can try this with me. N is a constant, take it out. E to the negative nx divided by negative n, that is the derivative of e to the negative nx. E to the negative nx, the antiderivative is e to the negative nx, and the chain rule, you have to divide by negative n. This you evaluate from 0 to x. Okay, so here's the antiderivative, or here's the answer of the integration. This n will cancel out, but you have the negative sign outside, this negative sign. When you evaluate e to the negative nx from 0 to x, when x is x, it is simply e to the negative nx minus, when x is 0, you have e to the 0. N times 0 is 0. But what is e to the 0? E to the 0 is 1. Therefore, your answer will be negative e to the negative nx minus 1. When you multiply by negative sign, you get 1 minus e to the negative nx. So this is the CDF of our sequence xn. Okay. This is the CDF of the exponential density. Now we'll use it in our limit, right? So what do we need? We need probability xn greater than or equal to epsilon. So that is 1 minus probability xn less than or equal to epsilon, right? So we have, let's replace this with the CDF. What is the CDF? 1 minus e to the negative n, and we have to evaluate x at where? X at epsilon, right? Remember, when you have fx, now this is fx. So when you have some number evaluated at x, this x, now in our case, it will be epsilon. So wherever you see the value x, you have to replace it with epsilon. So what is the answer? 1 minus 1 will cancel out. You have e to the negative n epsilon. Is this clear up to this point? What we did so far? Okay, so you have to show convergence in probability. We start with what we want to show. We want to show that the limit n goes to infinity, the probability xn minus 0 greater than or equal to epsilon equals 0. Since we have just minus 0, you can write probability xn greater than or equal to epsilon, omitting the absolute value because we know x's are all positive. This is the complement of the CDF. So derive the CDF. We found that it is 1 minus e to the negative nx. That is the CDF at x, or the cumulative probability at x. In our question, in our right-hand side, we have the probability xn greater than or equal to epsilon. So we replace x with epsilon, and we need 1 minus CDF. And when we do that, your final answer is e to the negative ne. Now let's go back and put it. Okay, so let's go back and put this in our limit, right? So let's see what will happen. Right, so we need the limit n goes to infinity, probability xn minus 0 greater than epsilon. Okay, that will be limit n goes to infinity, probability xn greater than or equal to epsilon. We found this quantity to be e to the negative ne. And if you write this with the negative sign at the bottom, you have 1 over e to the ne. And we see that when n goes to infinity, you have 1 over infinity. Okay, your n is at the denominator. When n goes to infinity, you'll end up with 1 over infinity. Okay, so you have this whole quantity goes to 0 as n goes to infinity. Why is that? Because your n is at the denominator. Okay, 1 over e to the n. When n goes to infinity, 1 over infinity is 0. So what do you have? You have that limit when n goes to infinity, the probability xn minus 0 greater than or equal to epsilon goes to 0. And that is exactly what we want to show. So this is exactly what we want to show. So we found that since we have the limit here, you can write equal sign there. So this means xn goes to 0 in probability. Okay, so those are the steps you have to follow. Is this clear to all of you, the steps we did? Any questions from this example? So what you have to remember is this red star. This is what you have to show. You have to show that limit n goes to infinity, probability, whatever the quantity greater than or equal to epsilon. Okay, then according to what you see in your right-hand side, you can proceed with the given information. In this question, it is about the probability x greater than epsilon. So you know that is the complement of the CDF. You know the PDF, so find the CDF and then use it in the limit. And you can easily see that that goes to 0 when n goes to infinity. Okay, any question about this one? So let's move on to the next one then. So here's the second one. Suppose you have a random variable x. And you have xn is x plus yn. Okay, now you have another random variable xn that is x plus yn, where the expectation of yn is 1 over n and the variance of yn is sigma square over n. And the sigma square, the sigma is greater than 0. Now obviously it should be, this is a standard deviation. Okay, and it's a constant. You want to, you have to show that xn goes to x in probability. Okay, you have to show that xn goes to x in probability. Now what do you know? You know there's a random variable called x. And then you know that there's another random variable or the sequence of random variable called xn, that is x plus yn. Yn is another sequence of random variable. It is given that the mean and the variance of the yn, that are, those are 1 over n and sigma square over n. So those are the information given to you. And again, we have to show that xn goes to x in probability. And there was another hint available with this question, that is about the triangular inequality. This is the triangular inequality for all a and b, which are real numbers. If you take the absolute value of a plus b, it is less than or equal to absolute value of a plus absolute value of b. Okay, this was given as a hint. So you know that you have to use it somewhere. Okay, again, so what you have to show is that xn goes to x in probability. What does that mean? We have to show that for epsilon greater than 0, limit n goes to infinity, probability xn minus, now what is the other, what do you subtract? The value that you see at the other side of the arrow. X. Probability xn minus x greater than epsilon is 0. This is what you have to show. Okay. Okay, now let's look at this xn minus x. What is it actually? Look at this given information. You have xn equals x plus yn. What does that mean? Xn minus x is what? Yn. So this is what you have to show. Xn minus x, which is yn. The absolute value of yn is greater than epsilon. That is what you have to show. Okay, so rather than writing this whole xn minus x, you can write n goes to infinity, probability, absolute value of yn greater than or equal to 8. Now here you can't omit the absolute value. We do not know anything about yn. What is the support of yn? It's not given. We even do not know the distribution. So you have to keep the absolute value. You have to show that this limit goes to 0. Okay. Now in this situation, you don't see any PDF, you don't know the CDF, nothing is there. The only additional information you know is about the expectation and the variance. Now, as soon as you see that there is information about the expectation and variance, the first thing that should come to your mind is you can use the Chebyshev's inequality to prove this convergence in probability. Okay. So whenever you see expectation and variance as given information for a certain problem, which asks you to show that the convergence in probability, which means you can use them with the Chebyshev's inequality. Okay. Now, can you remember the Chebyshev's inequality? Chebyshev's inequality has two forms. Okay. So I'll write it down here. Inequality. Okay. So if you have your notes, you can also check it and see whether you can find it. Chebyshev's inequality. That is the probability okay, so here's the first form. Probability x minus a greater than or equal to k. This is less than or equal to expectation of x minus a square divided by k square. This is one form. What is the other form? The other form is a special case where your a becomes the mean of x. Okay. So in that situation, you'll have probability x minus ex greater than or equal to k. That will be less than or equal to the variance of x divided by k square. So these are the two forms of Chebyshev's inequality. Okay, so these are the two forms of Chebyshev's inequality. Now in this question, since the variance and ex is given, this is the one we can use, the second form. Okay, the special situation where your a becomes the mean of the random variable x. Okay. So use Chebyshev's inequality. Now you have to write these things when you do a proof. Okay, do not just apply the Chebyshev's inequality straight away. Make sure you write this line. Use the Chebyshev's inequality with the expectation of yn and the variance of yn. Okay. Right. Now you can't use this straight away. What is the reason? The reason is in your limit, what you see is just the absolute value of yn. If you want to apply the Chebyshev's inequality, you have to have yn minus expected value of yn. Okay, but you don't have it in your left-hand side. That means you have to rearrange these terms. So your left-hand side, you have y minus ey. Okay, now how are we going to do that? Since these are inequalities, it is very easy. Now this is where you are going to use the triangular inequality. Okay, this is where you are going to use the triangular inequality. So let's use, so I'm going to use a few more letters to make it easy to understand. I'm using a letter A, that is yn minus expected value of yn, and B as the expected value of yn. Why am I using it? Because then we can use the triangular inequality. A plus B. What is A? Yn minus Eyn. B is Eyn. When you add A and plus, what is the answer? Your answer will be Yn minus Eyn plus Eyn. What is it? Eyn plus and minus will cancel out and you'll end up with Yn. And that is what we have in the left-hand side. Okay, so this is another trick. You add and subtract the same value. Okay, so you end up with the original value. Okay. But this is the absolute value of A plus B, and this becomes Yn. But according to the triangular inequality, this is less than or equal to A, absolute value of A plus absolute value of B. So that means we end up with the absolute value of Yn is less than or equal to what? What is A? A is Yn minus Eyn. Plus, what is B? B is Eyn. Okay. Is it clear up to this point? Applying the triangular inequality. So we are proceeding step by step to use the Chebyshev inequality, and using the Chebyshev inequality to prove the convergence in probability. Okay. Now these type of tricks you have to get with practice. Okay. Now let's see what will happen to this absolute value of Yn. Okay. So we have Yn minus expected value of Yn as it is. But what is the expected value of Yn? It is given that it is y over n. So you can replace this now expectation. Is it given any information about A is a constant? N is the number. Okay. So n is a number. So 1 over n, it is going to be positive. So it is 1 over n, a sample size. It is never negative. So you can omit the absolute value. It is 1 over n. Right. Now let's see how to prove the convergence. So we go back to our original, the limit probability xn minus x greater than or equal to epsilon. This is less than or equal to what? Okay, so I'll write so this is same as limit n goes to infinity probability yn greater than or equal to epsilon, but we saw that this is less than or equal to this is less than or equal to probability yn minus E by n. Okay, see this quantity plus (1 over n greater than or equal to epsilon). So instead of absolute value of yn, we put all these things inside the absolute value. Okay, so yn 1 over n is always positive, so you can put it outside the absolute value. Okay. Now let's rearrange this term. So it is now the less than or equal. From where do you get this inequality? From the triangular inequality, from the hint. Right. So this is less than probability yn minus E yn. And let's take this 1 over n to the other side. Okay. Right. And then we are going to apply the Chebyshev inequality. Right. What is the Chebyshev inequality? You have yn minus expected value of yn greater than or equal some value. Okay. Now expect epsilon minus 1 over n. It is we can say this is epsilon prime. Okay, so no problem. You can write it like that, but it is epsilon minus 1 over n. Now, according to the Chebyshev's inequality, what is this one? If you have probability x minus ex greater than k, what is it? It is less than or equal to. So the inequality is still continuing, the less than, so no problem. You have to write the variance of yn divided by what? The variance of yn divided by k square. What is our k now? Our k is epsilon minus 1 over n square. Okay. So I'll repeat. Now you have probability yn minus expected value of yn greater than or equal to epsilon minus 1 over n. But if you apply the Chebyshev's inequality, what do you have? You have variance of this quantity. What is the variance of yn? It is sigma square over n. See, it is given. The variance of yn is sigma square over n. And sigma square over n, and at the bottom you have epsilon 1 prime square. Okay, it doesn't matter, another epsilon. Okay, now what will happen to this? Now you have the limit here, right? So in front of this, all these things, write the limit n goes to infinity. Limit n goes to infinity. So what do you have? When n goes to infinity, your n is at the bottom. When n goes to infinity, you have 1 over infinity, which is going to be 0. And that is exactly what we want to show. So we have showed that the limit, the probability xn minus x greater than or equal to epsilon, that goes to 0. And that is exactly what you can do. So you get xn minus x, or you can say simply, therefore, xn goes in probability to x. Okay, so we have a question. Can't we solve it finding EYN square? So you mean by applying the other form of Chebyshev inequality, I guess, and find, okay, let me check it. Okay, yeah, that is also possible. If you want to find the expectation of yn square by using the variance and the mean, that is also possible. Yes, that is another method to do it. Okay, but are you using the triangular inequality in that case? Where are you applying the triangular inequality? Yeah, you are not using the triangular inequality. Let me check. Expectation of. So how do you say the probability yn greater than or equal to epsilon is less than or equal to EYN square? So here's the question. So PYN greater than or equal to epsilon. So this is less than or equal to okay, so that is from the other one, right? The Chebyshev inequality, the other form. So you use EYN square. And you find EYN square by using the computational formula, the variance of yn minus EYN whole thing square, right? So that is why, yes. Yes, that is also possible, right? So what is the variance of yn? Variance of yn is sigma square over n minus 1 over n square. So you have over n square, epsilon square. Okay, you have this n. So how do you say that it goes to, when n goes to infinity, how do you write this? You have to have all n's at the bottom, right? If you can rearrange this term, okay, so what you have in your left-hand side is n sigma square. Am I right? Okay. So you have to show that this goes to 0 as n goes to infinity. So you have to rearrange this somehow. This n, all n's are at the bottom. Otherwise, you can't say it goes to 0 as n goes to infinity, right? So you have a problem there, right? I think if you use this one, there is an extra n at the numerator where you have a problem, right? Right, so double check this one. Okay, if you can rearrange all the terms so that n's are at the bottom, then no problem. Okay, or at least if you write it with the n at the bottom, again you will get 1 n at 1, right? So it is not, I don't know, try it. Okay, if you can write all the n's at the bottom, so when n goes to infinity, the expression goes to 0, then this way is also okay, right? But if you cannot do that because of this n at the numerator, there is a problem, right? And there's another question: when we are given a hint, should we definitely use it? The hints are given to make your calculations easy, okay? But if you can do it without the hint, maybe it will be a longer way or a familiar way to you. That's no problem with that, okay? No problem with that, and you can proceed with your way without using the hint, okay? Okay, can we both the numerator divide by n square? If you do that, can you do it? Okay, if you do it and get it, then no problem. If you can get n at the bottom, no problem. That is also okay, right? Yeah. Any other question from this one? Okay. Shall we move on to the next one then? Okay, so here's the third example. Consider a sequence xn for n going from 1 up to infinity such that, now this is how you define xn now. Xn will be n square with probability 1 over n. This is a little bit different question. Or it will be 0 with probability 1 minus 1 over n. So the total probability is 1. Xn can be either n square or 0. It will be n square with probability 1 over n and 0 with the complement 1 minus 1 over n. We have to show that xn goes to 0 in probability. Okay. We have to show that xn goes to 0 in probability. So we start with our familiar expression. You have to show that for epsilon greater than 0, what do we have to show? The limit n goes to infinity, probability xn minus, now you see 0 here, greater than or equal to epsilon goes to 0. So that will be limit n goes to infinity, probability. Since you have again xn minus 0, you can simply write xn greater than or equal to epsilon, right? So what do you see here now? So you see that the probability xn greater than or equal to epsilon. What is epsilon? Epsilon is always greater than 0. Okay. So if you have xn values greater than 0, what is that value? What do you see in the given information? Okay, for when epsilon is greater than 0, and when you have to find xn also greater than epsilon, that means okay, it should be greater than 0. That will be this value for xn. So xn will contain n square. So you can write this as the probability xn greater than or equal to epsilon means your xn is equal to n square. Otherwise, it is 0. So you can replace xn greater than epsilon by n square because it is given that xn can be either n square or 0. Okay, so you cannot be 0 because your epsilon is greater than 0, right? So therefore, you'll end up with xn equals n square. And what is this probability? The probability xn equals n square is 1 over n. So simply you end up with n goes to infinity 1 over n. So very easily you can see that this goes to 0. Okay, so this is a very small question. Okay, the only thing is you have to understand that this probability is same as xn equals n square. Okay, that's all you have to figure out. The rest is just very simple. Okay. Right. Is this okay? Anything unclear? Right. Right. So that is a smaller one. Now let's do the next example. Now suppose xn and yn. Now you have two sequences. The two sequences of random variables defined on the sample spaces. Some sample space. Same sample space shared by both xn and yn. Okay. And it is given that xn goes to x in probability and yn goes to y in probability. This is known. Okay, you know that xn converges to x in probability and yn converges to y in probability. That is given. You have to prove that the summation xn plus yn goes in probability to x plus y. Okay, so you have to show that the sum of xn and yn goes to probability in sum of x and y. Right. So this is again very easy one where you have to apply only the definitions of the convergence in probability. Okay, very small trick, then you will be done. Okay, so let's use the information given. When xn goes to x in probability, what do you know? What is the definition? That means when n goes to infinity, probability xn minus x greater than or equal to epsilon is 0. That we know. Now, since we are going to add two things, rather than using epsilon, I'm going to use epsilon over 2. So you can always, rearrange this epsilon term, okay, so that your answer is, you can arrange your answer in the familiar way. So I'm going to do epsilon divided by 2. And I'm going to do the next one also. When yn goes in probability to x, what do you get? You get limit n goes to infinity, probability yn minus y greater than or equal to epsilon over 2. Now remember, epsilon over 2 is another epsilon, let's say epsilon prime or something, right? So that is also 0. This we know because it's given that they converge in probability. Now what do we have to show? We have to show that limit n goes to infinity, probability xn plus yn minus what do you have in the other side of the arrow, x plus y. This is greater than or equal to epsilon equals 0. This is what we have to show. Right. So we'll use rewrite or rearrange the probability term and see how we can apply the things that we know. Okay. So I'm going to write this probability as, now you have xn plus yn minus x minus y, right? So this minus value is for both x plus y. So I'm going to write this as xn minus x, okay, plus yn minus y, right? I can do that. And still you have this greater than or equal to epsilon, okay? So this is our left-hand side. Now what is this? Okay, since these are random variables on the same spaces, you can split this into the two limits. How can you do that? You can write this as the probability xn minus x greater than or equal to epsilon over 2 plus limit n goes to infinity probability yn minus y greater than or equal to epsilon 2. How do you do that? By dividing this, writing this as epsilon over 2 plus epsilon over 2. Okay, so we split it into 2. And what do we know about this limit? We know that it goes to 0, okay, from 1. It's to 0 from 1. This goes to 0 from 2. So what does that mean? The whole expression goes to 0 as n goes to infinity. So that means xn plus yn goes to x plus y in probability, right? So here you are not using any of the other inequalities, Chebyshev's law, or any other thing, the PDFs, nothing. Simply rearranging the terms with the epsilon. Then you can easily find the answer. Okay. So I guess that is not hard. So that is question number 4. Please stop me if you want to repeat or any explanations, okay? Right, let's move on to the 5th example. Let yn is a sequence of random variables and a is a constant. So you have a sequence of random variables yn and a, which is a constant, such that the expectation of yn goes to a and the variance of yn goes to 0 as n goes to infinity. Now there is a difference between EYN equals 0 and EYN goes to, EYN goes to A. Okay, now EYN equals A and EYN goes to A. Now they are not the same, right? So this is when n goes to infinity, EYN converges to A. The variance converges to 0 as n goes to infinity. Okay, so that is the given information. You have to show that this yn converges in probability to A. Okay, so as n goes to infinity, that is what you have to show. So again, we stick with our usual definition. And as I mentioned, as soon as you see expectation and variance, what is the inequality that you are going to use in this proof? As soon as you see expectation and variance, what can you use? What is the inequality that you are going to use here? You have to use the Chebyshev's, okay, the Chebyshev's inequality, right? Okay, so let's use it. We have to show that the probability yn minus what you have in the other side of the arrow is a greater than or equal to epsilon is 0. Limit n goes to infinity. Okay, so let's start with the left-hand side and see whether you can show that the right-hand side is 0. So I suppose you are also doing these examples with me, right? If I am too fast, let me know. Okay. And okay, so we have yn minus a. what is yn? What is a? When limit n goes to infinity, a goes. What is a? A is e by n. Okay, so the limit is e by n. Right. So we have the Chebyshev inequality straight away in our right hand side. Okay, so you can write this as the less than or equal to variance of yn divided by epsilon square. So this is like our k, and we have the everything as the Chebyshev inequality. So make sure you write it. You state why you write this next line with the inequality. Why? Because it is from the Chebyshev inequality. So make sure to note it down, okay, in your answer script. From the Chebyshev inequality, you can say that the variance of this is less than or equal to variance of yn over epsilon square. And what do we know about the variance of yn? It says it goes to 0 as n goes to infinity. So this whole left, the right hand side goes to 0 as n goes to infinity. Why? Because variance of yn goes to 0 as n goes to infinity. So it doesn't matter what you have at the bottom. When your numerator goes to 0, everything goes to 0. So which means you can say yn goes to a in probability. Okay. Now, by now, since we have done about 5 questions, now you can see the pattern, right? It's the same thing that you do. Okay. So you have to show this thing. In order to show that, look at what you have here. If the information given is about expectation and variance, use the Chebyshev inequality. You can very easily get the answer. If you can't see the Chebyshev inequality straight away, you can add and subtract certain terms and then make it look like the Chebyshev inequality, rearrange the terms. Okay, you will be able to do that with the given information. Or if the PDF or the CDFs are given, then you can proceed with the definition of the CDF, and you can very easily show that the probability goes to the convergence in the probability. Okay, so those are the only things that you have to do. Right? The thing is you have to figure out what is the method you are using. Okay, so you will be get very familiar after using it. Okay, so we have a question: can't we use the Markus inequality? The Markus inequality is what is it? The Markus inequality is, let's write it down so everybody can see it. Let A be non-negative continuous random variable, X be non-negative for any constant A, probability X greater than or equal to A is less than or equal to EX over A. So this is the Markus inequality, right? Here you have, okay, so how do you arrange this to look like this? So you have to have yn greater than or equal to A, right? What you have is yn minus A greater than or equal to epsilon. Okay, so in that situation, this will be possible if you have yn minus 0 greater than or equal to epsilon. And in that case, you have yn greater than epsilon. Okay, so in that situation, you can write this is less than or equal to E by n divided by epsilon square. But what you have yn minus A. So it is not same as the Markus inequality, right? Can you see the difference? Xn greater than or equal to A. Now in this Markus inequality, your A is like your epsilon, okay? In this definition, A is like the epsilon. Okay, but you have yn minus A, okay, something extra, and it is within the absolute value side, okay? So, in this, in order to apply the Markus inequality, it says these x's, they are non-negative. So you cannot have the negative values. In this question, it says yn is a sequence of random variables. There's nothing about whether it is positive or negative, because you have the absolute value sign. You can't drop it without knowing that yns are all non-negative. Okay, so therefore, the Markus inequality, it is not applicable here because you don't have all the necessary information. Okay, so you have to go for the Chebyshev inequality. Is it okay? Right? Any other question? Right, let's go to the next question. Before we do the next question, I will give you some information. You already know these things, but just to recall, okay? Now, suppose your Sn means sum of x1, x2 up to xn. Okay, sometimes we use Tn, that's for total, or sometimes Sn for the sum. So Sn or Tn, that is the sum of your x's. So let's say xi, I going from 1 to n, okay? Now, if xi's are independent, we can come up with very nice findings, okay? What will be the expected value of Sn? How do you write the expected value of Sn? That will be the expected value of x1 plus x2 up to xn. Even without independence, you can write this as ex1 plus ex2 all the way up to exn, which means sum of exi I from 1 to n. Okay. And how do you write the variance of Sn? If they are independent, this will be the variance of x1 plus x2 all the way up to xn. Since they are independent, you can write variance of x1 plus variance of x2 plus up to the variance of xn. And then you'll end up with sum of variance of xi I from 1 to n. In general, that means we do not know whether they are independent or not. Okay. If independence is not assumed, what will happen to this variance? Can you just write the variance of x1 plus x2, variance of x2 and so on? What will happen to the variance if they are not independent? What is the other term that will come into the equation? Yeah, the covariance, exactly. So what will happen if they are not independent, or if it's not known that they are independent, you will end up with the variance of xi. In addition to that, you will have the covariance of each and every pair xi, xj, the sum of these covariances where I not equal to j. When I equal to j, covariance of xi and xi, that is same as the variance. So variance, when I equals to j, they will be covered from the variance. In other cases, you have plus covariance xi and xj. Okay. So this is something you already know, but you may need it when you answer the next question. Okay. So this will be the last question on the convergence. Okay. So I'll do the convergence in probability when it comes to some questions in the exam paper, right? So here's the next question. We have x1 up to xn, be IID. So what is IID? Independent and identically distributed. So they are independent. Identically distributed means all x1 up to xn, they share the same probability distribution. If x1 is normal, that means all the others are also normal. Okay, same means same variance, identical. Okay. IID random variables with The expectation of each of these xi's are mu, and the variances of each of these xi's are sigma square. Okay, this is a finite variance. Okay, so not less than infinity means these are finite variance. Okay, and we are going to define the term Sn, which is x1 plus x2 plus xn. Okay. Then Sn over n goes to mu in probability. Okay. And if you define a random variable yn, which is our Sn over n, okay, we know that the expectation of yn, what is the expectation of yn? That is the expectation of Sn over n. Okay. The expectation of Sn is what? Expectation of Sn is the expectation of x1 up to xn divided by n is a constant, so you can take it out. And each of these expectation x's, they have the same mu. So you have mu plus mu plus mu. How many times? There are n number of mu's because there are n terms. So you have n times mu over n, which is mu. So the expectation of yn or expectation of Sn over n is mu. In the similar manner, let's see variance of yn. What is it? What is the variance of yn? Yn is Sn over n. So we defined it. And when you have a constant, when you take outside the variance, it becomes square. So you have 1 over n square variance of Sn. Since they are IID, right? So that will be the sum of the variances. So how many sigmas are there? N of them. Sigma square times n. Right? So you have n square, 1 n will cancel out. You will end up with sigma square over n. Okay. Now, what is this actually? Expectation of yn equals mu, variance of yn equals sigma square over n. What is this actually? What is yn? Yn is what? This is the sample mean, right? Yn is the sample mean. Why? You take the total divided by n. So that is the mean. And you know that from the sampling distribution of sample mean, the mean of the sampling distribution of sample mean is mu, and its variance is sigma square over n. So this is exactly the way how you show the sampling distribution of sample mean. It is mu and sigma square over n. Okay. So this is something extra that I wanted to show you. Okay. Our question is now, show that this is what you have to show. Show that Sn over n goes to mu in probability. Okay, so we have to show, write it again. We have to show that Sn over n is what? Yn. Yn goes to mu in probability. Okay, so this is what we have to show. Okay, now you know what to do. You have to show, what do you have to show? You have to show limit n goes to infinity, probability, absolute value yn minus mu greater than or equal to epsilon equals 0. This is what we do all the time. Now again, what do you see here? Chebyshev's inequality. But straight away you see the Chebyshev's inequality, right? So what will happen? This limit n goes to infinity, yn minus mu greater than or equal to epsilon. This is less than or equal to variance of yn divided by epsilon square. Why? Chebyshev's inequality. Make sure you write it. Okay, Chebyshev's inequality. And where do you, how do you find the variance of yn? We already found it here. Okay, so that is why I did it here. But when you do the question, when you come to this part, here also you can find the variance of yn. Okay, the variance of yn is the variance of Sn over n, and you can proceed with the given information. Everything is given. So you know that the variance of yn is sigma square over n, and you have this epsilon square. And it is very clear that this goes to 0 as n goes to infinity, because n is at the denominator. Okay. So what does that mean? Yn goes to mu in probability. Okay. So this question is not that much hard. The only thing is just finding this variance of yn using the given information. So you should have the the knowledge about when they are independent. You can write the variance by adding the individual variances like this. Okay, and you'll end up with this sigma square over n. Okay, so if you can get this number and know that Eyn is mu. Okay, so you can use this Chebyshev inequality because you know that mu is Eyn, right? If you don't have the Eyn here, you can't use the Chebyshev inequality. But here it is exactly Eyn because you know that it is mu, right? So that is why you can apply the Chebyshev inequality. Okay. So I guess that is not a very hard question, right? We can easily show the convergence in probability. Okay, so those are the questions I selected. Okay, I think they almost covered many of the past paper questions or very similar to them, right? So if you have any doubts, I guess now you can refer to these examples and easily understand it, right? And now I'm going to start some of the selected past papers, and when we do that, we will be using some central limit theorem. Okay, examples from the central limit theorem. Any questions so far? Okay. Right. So here's the first question. I chose this from the pool of questions from 2015 final exam. Maybe it was there in the paper or maybe not. Right? So these are the candidate questions for 2015. Okay, so one request, can you explain question 3 again? Okay, let me get it back. Question 3. Okay, this one. Right, I'll go over the what we did again. Right, I guess up to what we have to show that it's okay. Right. Now, when you look at this given information, this is not the PDF, okay, of xn. This is not the PDF of xn. It says that the values xn can contain. Xn can be either n square or it will be the 0. Okay. Now, if your sample size is, let's say 10, then it will be 100 with probability 1 over 100. Okay, so this is with 1 over 10. If your sample size is say 5, the xn will contain values 25 with probability 1 over 5. Okay, so what does that mean? If n is 5, okay, what are the values that x can have? The values that x can have is n square. That is, x will be 25. Okay. Since n is 5, x will have 5 numbers. All of them have the value of 25, and the probability that it is 25 is 1 over 5. Probability is 1 over 5. Okay, so if I write it again, the probability x1 is 25 is 1 over 5. Probability x2 equals 25 is 1 over 5. So likewise, up to x5, probability x5 equals 25 is 1 over 5. And since the sample size is 5, when you add 1 over 5 times, you get the total probability 1. Okay, or the value of xn is 0 otherwise, right? So what does that mean? Probability x1 equals 25, 1 over 5. The probability that x1 equals 0, what is it? 4 over 5. Okay, so likewise, you can write the complements also one by one. Okay, that's just to explain the idea of this given information. Now you have to show that xn goes to 0 in probability, right? Again, that means you have to show limit n goes to infinity p xn minus 0 greater than or equal to epsilon. Since you have minus 0, you can omit it and write xn greater than or equal to epsilon. Okay, now look at the values of xn. What are the values that xn can get? Either it is 0 or n square. Okay, either it is 0 or n square. Okay, those are the only two possibilities. It says that the xn is greater than or equal to epsilon, but whenever we choose this epsilon, we say this epsilon is greater than 0. Okay, so that is the way we prove the theorems. Whenever you use epsilon, we write for all epsilon greater than 0, and that is how we proceed. Okay, that is how these inequalities are developed. So epsilon is greater than 0. Okay, that means the probability xn is also greater than 0. So that means this cannot happen. Xn is greater than 0. So what is the only possibility? It should be n square. So the probability, this xn greater than or equal to or greater than 0 means it is always n square. That is the only possibility. So you can write this. This is same as the probability xn equals n square. And what is this probability? It's probability 1 over n. So this probability is simply 1 over n. And when n goes to infinity, 1 over n goes to 0. Okay? Right. Okay, so I think that's clear. So there's another question. If we have xn minus x term, when we use Chebyshev's inequality, is this x should be constant or mean? Now there are two versions of Chebyshev's inequality, right? There are two versions. See, one is the a is constant, the other is a is ex. A is ax minus a. This first one is the original Chebyshev's inequality, and this is a special case where your a becomes ex, right? Okay, so when you have x minus a certain constant here, okay, so when you have a certain constant here, then you use this the first Chebyshev's inequality. Okay, so those are two things, right? So one can be when you have xn minus x, it cannot be because x is a random variable. But when x is like a, b, or some number c or some number, then you can use the Chebyshev's inequality, the first one. But when this a becomes the expected value, then obviously that is the second form of Chebyshev's inequality. Okay, is that clear? Okay, right. Any other questions? Right. Okay, then let's move on to the previous exam papers. Right. So look at this question. A box contains 3 balls labeled 1, 2, and 3. Two balls are randomly drawn from the box 1 at a time without replacement, right? Sorry. You randomly draw two balls from the box 1 at a time without replacement. Okay, you take one, you don't put it back, and you take the second one. Let X be the number on the first ball and Y be the number on the second ball. You have to derive the joint probability mass function of Pmf of X and Y. Okay. Right. So what are the possible values X and Y can get? X is the number on the ball, the first one. Y is the number on the second ball. X can be either 1, 2, or 3. Y can be also 1, 2, or 3. But since you are not replacing, if X got 1, the first ball in the first row, since you are not going to replace it, it is not available for the second row. Okay, so we'll see how we can get these probabilities, right? So it is very easy if you draw a simple tree diagram to get these probabilities. Okay, so this is the first row, and then you have the second row. When it's the first row, it can be either the second, the ball 1, 2, or 3. And since all of them have the same chance, it will be 1/3. What about the second one? If the first one is 1, the second cannot be cannot be 1 again, because we are not going to put it back. Okay, so the second row will have only two possibilities. Either it will be 2, even first is 1, or either it will be 3, even 1. And what is these probabilities? Since you have only two balls, it will be just 1/2, 1/2. When it comes to if the first one was the second ball, then the second can be either 1 or either 3. Okay, you cannot have 2 because it's already drawn and it was not put into the box again without replacement, right? And what about this one? 3 is already gone, so it will be either 1 or 2, given first is 3. So what is this part? That is the probability. The first ball is 1, second is 2. What is that probability? 1/3 times 1/2, 1/6. The second one is probability that the first ball is 2, second ball is, the first ball is 1. Still we are in this part. First is 1 and the second is 3. So likewise, you can fill all these 6 possibilities. 2 and 1. 2 and 3, 3 and 1, 3 and 2, right? And if you add all these probabilities, 1/6, 6 times, you get total probability 1. Now let's write down the Pmf of X and Y, right? The joint Pmf of X and Y. So this is my X, the first ball. This is Y, the second ball. Can be either 1, 2, or 3. 1, 2, or 3. 1, 1 never will happen. First is 2 and second is 1. Where is it? First is 2 and second is 1. Here it is, 1/6. So you'll see that all these are 1/6. First 2 and second 1. 2, 2 cannot happen. 0. So that is our Pmf. Okay, so you can easily find it. Now, what is the marginal Pmfs of X and Y? We can use the same table. These are my X's. Okay. So if you find the marginal densities, what will be this one? This is the Y. When Y is 1, you have 2/3, you add 1/6 plus 1/6. And when Y is 2, again, 1/6 plus 1/6. And again, this one is, 2/6, 2/6, 2/6, which will be 1/3, 1/3, and 1/3. So altogether, you have the total probability 1. So Py is a proper Pmf. And then you can have the marginal density of X. Very similarly, it will be 1/3, 1/3, and 1/3. Total probability 1. Okay. And then you have to find the conditional density function of y given x equals 1. And then you have to calculate the probability y greater than or equal to 2 given x equals 1, right? So we'll use this one, the conditional density of y given x equals 1. So we are going to consider x equals 1. It is given that x equals 1. So this is what we need. When y is 1, what will be the probability when x is given x is 1? So how do you find it? Right, the conditional density, the probability y given x equals 1, you find it by finding the joint density divided by the given one when x equals 1. So what is the probability when x equals 1? That is 1/3. So each of these joint densities, you have to divide it by 1/3. So let's write it down. Y given x equals 1, y will be 1, 2, or 3. So joint density of x and 1, when x is 1, y is 1. What is it? 0. 0 divided by the given one, probability x equals 1 is 1/3. So this will be 0. The next one, y2, x1, the joint density, the joint probability is 1/6 divided by p x equals 1 is 1/3. Right? So that will be 1/2. Similarly, when y equals 3, x equals 1 and y equals 3, the joint density is 1/6. 1/6 divided by the given probability, which is 1/3, again 1/2. So you have the conditional density of y given x equals 1. Okay. And again, when you add these probabilities, they add up to 1. So this is a correct PMF. And finally, you have to find the probability y greater than or equal to 2 given x equals 1. So y greater than or equal to 2, it will be this one and this one. So what is it? It is exactly 1. Add these two probabilities, which is 1. And so that is not a hard question. The only thing is you should be able to figure out these probabilities and prepare the PMF. And then based on the PMF, you will answer the question. Now, what will happen if you end up with the wrong PMF, joint PMF? If your joint PMF is wrong, your marginal PMFs are wrong, your conditional densities are wrong, and your probabilities are wrong. Now, what will happen? Will you lose all the marks? Well, I usually don't do that. If you end up with some mistakes in part A, which is deriving the joint PMF, you will lose marks for that, those errors. But when you find the marginals, you are doing it based on your answer. So after that, I only look at the method. So if you have shown that you know how to find the marginal densities, you will receive partial credit. You will lose only marks for this wrong PMF in part A, but the rest, if I can see that you know how to find it, although you'll end up with the wrong answer for PY and PX because your joint PMF is wrong, you won't lose marks, okay? And even the conditional density, based on your answer of part A, if I can see that it is correct, you will get partial credit, okay? What about part B? If another random variable u is defined as x plus y, find the PMF of u. Okay, now that is the transformation, right? Your u is x plus y. Now this is a mass function or a discrete case, right? So we'll see what are the possible u values, x plus y. What are the possible combinations? You can have 1 and 2. You can have 1 and 3. 1 and 1 is not possible because it is the probability is 0. Then you have 2 and 1. You can have 2 and 3. Then you can have 3 and 1. And you can have 3 and 2. So these are the possible combinations of x and y. And what is u? If x is 1 and y is 2, u is 3. In this case, u is 3 plus 1, 4. 2 plus 1, 3. 2 plus 3, 5. 3 plus 1, 4. 3 plus 2, 5. So what are the possible values? 3, 4, or 5. So let's write down it. You can be either 3, 4, or 5. 3 appears how many in how many places? You see 3 in 2 places, right? Out of 6. 2 out of 6 probability of 0. 4 appears again in 2 places out of 6. 5 appears again in 2 places out of 6. So that is 1/3, 1/3, 1/3. So that is the PMF of U, right? Okay, any question about this one? Right, so let's move on to the next question. Right. So this is about the transformations with the Jacobian, comes under chapter 3. Let the random variable x1 and x2 have the joint probability density function given in this fx2. And look at the support of x1 and x2, they are depending. Okay, so these are not independent random variables. Suppose y1 is x1 over x2 and y2 is x2. You have to find the joint probability density of y1 and y2. Okay, so here you are going to use the transformation method to find the joint probability density of the 2 new random variables y1 and y2. y1 is x1 over x2, y2 is x2. Okay, so what is the first step? You have to write, well, you have to find the inverse functions. That means you have to write down x in terms of y, x1 in terms of y1 and y2, x2 also in terms of y1 and y2. So let's do that. When y2 equals x2, that means x2 is y2. So that is easy. What is x1? x1 is y1 times x2, but x2 is y2. So x1 is y1, y2. So you have x1 and x2 in y1 and y2. Okay, so these are the inverse functions. Now what is the next thing you have to do? You have to find the Jacobian. Why? You have to find the joint density of y1 and y2. How do you find it? According to the transformation method, that will be f x1 and x2 evaluated at y1 and y2, or you can write the inverses, okay, the inverse functions, and you have to multiply it by the Jacobian, right? So that means you have to find the Jacobian first. Okay, so let's find the Jacobian. Can you remember how to do that? Del by x1 over del by y1, del by x2 over del by y1, del by x1 over del by y2, del by x2 over del by y2. Okay, so let's find it. What is x1? y1, y2, del by y1. x2 is del by y2 over del by y1. Again, x1 is del by y1, del by y2, del by y2. x2 is y2. Right, so these are the partial derivatives. When you do the derivative with respect to y1, y2 is like a constant. So y1 times y2, the derivative with respect to y1 will be simply the constant y2. From this one, y2 derivative with respect to y1 is like a constant, so 0. y1, y2, the derivative with respect to y2, y1 is like a constant, so it will be y1, and this will be, sorry, this is y2, 1. And how do you find the determinant? You cross multiply y2 times 1 minus y1 times 0, so this is 0. You'll end up with y2 as the Jacobian. Okay, so Jacobian is y2. Now let's apply it to the PDF. So do you have enough space to do everything? It seems like not. Anyway, we'll try. So what is our f by 1 by 2? That will be 10 times x1. But what is our x1? x1 is y1, y2. So you have to write y1, y2. And then you have x2 square. What is x2? x2 is y2. So you have y2 square multiplied by the Jacobian. Let's find the support later, right? Let's see what will be the support. So what is the answer? If you simplify this, this will be 10 times y1, y2 to power 4, right? And we'll see how we can get rid of this absolute value, right? That means we have to look at the support. Okay, so what do we know about the supports? We know that the support of x1 and x2 is what is given as the support. So let's write down them. What is x1? x1 is y1, y2. Okay, and from x1 less than x2, what do you get? You have y1, y2 less than y2. And then x2 less than 1 means y2 less than 1. Okay. So from this, what can you get? We know that y2 is less than 1. Therefore, from the first one and the last one, you can easily see that y1 is less than or equal to, the y1 is in between 0 and 1. Y is less than 0 and y2 is less than 1. So from this, you can say that y1 is in between 0 and 1. And what about y2? Again, the same thing. Y2 is less than 0 and it is less than y2, but y2 is less than 1. So which means y2 is also in between 0 and 1. Therefore, you can see that y2 is not negative. Therefore, you can omit this absolute value and you can write the joint density as 10 times y1, y2 to power 4. These are the supports. 0 otherwise. Okay, so you can write down the joint density, and that is the first part. And then you have to find the marginal densities of y1 and y2. How do you do that? I don't have enough space. Anyway, we'll see. How do you find the marginal density of y1? You have to integrate the joint density. Okay, if you need fy1, you have to get rid of the other variable. So y2 integrate from 0 to 1. What is the answer? You are integrating with respect to y2, so y1 is like a constant, so you can take that out. y2 to power 4, when you do the antiderivative, that will be 5. We'll do it from 0 to 1, this will cancel out, you'll end up with 2y1. So the density of y1, the marginal density of y1 will be 2 times y1. And similarly, you can find fy2. How do you do that? Integrate the joint density from 0 to 1, but do the integration with respect to dy1, right? And if you do that, you will find it is 5y24. Okay, I don't have enough space, but you can try this one. You'll see that this is 5 times y25. Okay, and if you look at these two numbers, when you multiply them, you get the exact joint density. So what does that mean? The joint density is the product of the marginals. What does that mean? y1 and y2 are independent. Okay, so you can say that that is the part C. Okay, so please try this one. The marginal density of y2. Okay. Right. So this is covering this is from chapter 3. Okay. Okay. Now we come to the order statistics, right, and also the convergence in distribution of the order statistics, right. So look at this question again from 2015. X1 up to xn be a random sample from uniform 0 theta. Okay. So when you see uniform 0 theta, you know that this is 1 over theta, right? And what is the fx? You have to integrate 1 over theta dx from 0 to theta. And if you do that, 0 to x, if you do that, you'll end up with x over theta. Okay, so the PDF and the CDF, you have to find it from the uniform density. Okay. And again, usually the PDF and the PDF will be given for the uniform density for any A and B. So according to your question, you can figure this out, and you can easily find the CDF by integrating from lower limit up to X, right? Now the question is the maximum of Xn. Yn is the max of Xn. You have to derive the CDF of Yn. Okay, so let's derive the CDF of Yn. Now, when you have to derive it, you have to start from the sketch. Okay, you have to start from the sketch. The PDF of the CDF of Yn is capital F Yn. So this is the probability Yn less than or equal to Y, right? Which is when Yn is the maximum. What do you know? All the others are also, if maximum is less than or equal to Y, the rest should be obviously less than or equal to Y. Therefore, X1 is also less than or equal to Y, right? X2 is also less than or equal to Y, because it is the when it comes to order stat. Can you remember order statistics, the minimum and the maximum, right? You know the minimum and the maximum. When the maximum is less than some number, obviously all the others are less than that number, right? So all the way up to Xn. Okay, now remember this notation. X1, X2 up to Xn is the random variable. When you order them, you write the notation like this. And the order statistics, we write them as Y1, Y2, Y3, Yn, right? So Yn is the maximum. Say for example, this is your sample of numbers. Okay, and your Y is say 25. What is the maximum of this data set? 20. Okay, if the 20 is less than 25, obviously 1 is less than 25, 3 is also less than 25, all the others are less than 25, right? And since this is a random sample, what will happen is you can write this as separately the probabilities. Now what will happen? This is same as the CDF. This is the definition of the CDF. X1, X2. Since they are all uniform, they have the same same CDF. What is the CDF? The CDF is X over theta. Now instead of X, what we have is Y. So X becomes Y. Y over theta, how many times? N times, right? So this is the CDF of Yn. So you can write if Yny equals 0, if when Y is less than 0, Y over theta to power n. When Y is in between 0 and theta, it is 1. When Y is greater than theta. So this is how you write the CDF in the correct way. Okay. And when you know the CDF, you can derive the PDF. How do you do that? Get the first derivative with respect to Y. Right? So d over dy, Y over theta to power n. That is it. N times Y over theta to power n minus 1. And then you go inside and get the derivative of Y over theta. So what do you get? N times Y over theta to n minus 1, 1 over theta. So this is the PDF, and you have to write it in the correct manner. This is when Y is in between 0 and theta, 0 otherwise. Okay. Now in this question, the deriving the PDF and the CDF of the maximum, it says to derive, okay, not to just write down. So you cannot just memorize the CDF and the PDF of the maximum and use that equation and substitute the values. You can't do it. When it says derive, you have to show all the steps and derive it. Okay, you have to show all the steps and derive it. So this is exactly, and okay, this is what we know the maximum, the CDF of the maximum. Okay, and the PDF of the maximum is what? N times fxy n minus 1 fxy, right? So this is exactly what you have, but you have to show it. You have to derive it, okay? Now, since you know the PDF of yn, you can find the expectation of yn, okay? So use the definition of yn. What is it? Eyn, that will be y. This the random variable is y times n y over theta n minus 1 over theta dy, y from 0 to theta, okay? Now you can simplify this one, 0 to theta. So you have this y and n minus 1 y will cancel out. You will end up with 1 yn, and n is outside. And theta n minus 1 and another theta, you will end up with theta to power n. Right? Okay, so n and theta to n outside, 0 to theta, yn dy. This will be yn plus 1 over n plus 1, and outside you have n over theta n. Right, so you can, and y evaluate from where to where, 0 to theta. So this will be theta n plus 1 n over theta n. Okay, so you can cancel the things. Which will give you 1 theta n and theta n plus 1 have just theta n over n plus 1. Right, so you can find the expected value of yn. Okay, any questions so far? Okay, so the next thing is to show that the yn goes to theta in probability, right? Now you know how to proceed, okay? The expectation of yn is there. You have to show that limit n goes to infinity, yn minus theta is equals 0. Okay, now in this case, you have theta is not the expectation. So in this one, you can use the Chebyshev inequality, the usual one, because theta is a number, right? Theta is a number. So you can use the very first or the original Chebyshev inequality, which will be the probability x minus a greater than or equal to k is e x minus a square over k square, right? So instead of epsilon k, you have the epsilon, and you have to show limit n goes to this is less than or equal to expectation of x minus theta square over epsilon. Okay. Now this one you have to find it again, right? So I'll guide you how to do it, but you can try it by yourself. You have to find the expectation of x minus theta square. Okay, how do you find it? In our case, what we have is y. right? So you can find y minus theta square multiplying by the PDF of the maximum yn integrated from 0 to theta ui. So I have to do this integration and find the answer and put it here, and you'll see that there will be a 1 over n term, and when n goes to infinity, it will go to infinity. So you have to find this one, okay? You know fyn, what is it? This one, you know this one. Multiply this by y minus theta square, okay? Y minus theta square multiplied by the PDF of yn and integrate it from 0 to theta, you'll end up with a certain expression, okay, similar to this one. And then you have to arrange the terms so that all the n's are at the bottom. Then you can show that the convergence in probability, okay? Right. I think as the answer you will get, when you find this, you will get 2 theta square over n plus 1, n plus 2. Okay, check this. So all the n's are at the bottom. See whether you can get this answer. And you can show that n goes to infinity. This expression goes to 0. Okay. Right. Okay, the next question is about the moment generating functions. Again, the transformations using moment generating function. Okay, so we have only 10 minutes. So obviously we have to do another discussion, right? Because we didn't come to the questions where we have the central limit theorem yet. Okay, so I guess we have to have another discussion another day. Okay, anyway, let's finish this one and see how we can find the answer. X and y are independent Poisson random variables with parameters theta and lambda. So write them. What do you know? X is Poisson theta, y is Poisson lambda. And it says that x and y are independent. Okay, so this is very important. You have to show that the random variable v, what is v? The sum of x and y. It is also Poisson with the parameter theta plus lambda. As a hint, it's given the moment generating function, the moment generating function of the Poisson random variable, right? So here's the Poisson distribution. The moment generating function is also given. Okay, so let's write down the, now what do you know about the, when you have two independent variables? Okay, so your v equals x plus y. And if you want to find the moment generating function of v, how can you do that? When x and y are independent, this will be what? The product of mxt, myt. Okay, so that is a theorem that we know from the properties of moment generating functions. Okay, when v is x plus y and when they are independent, the moment generating function of x plus y is the product of the individual moment generating functions. Okay, so let's write them down. When x has theta, so you have e to the theta, e to the t minus 1 times, when y is lambda, you have e to the lambda, e to the t minus 1. Okay. Now let's rearrange the terms. What do you get? You have e to the theta plus lambda, e to the t minus 1 is common. So what is this? This is the, you know, the moment generating function. It is the uniqueness property. So this is again the form of a Poisson distribution. And you can clearly see that this is the new parameter theta plus lambda. So which means we will follow Poisson distribution with theta plus lambda. So this is the new parameter. Okay, so that is what we have to show. Okay, so that's done. Then you have to find the PDF of x given y. You have to find the PDF of the x given y. How do you do that? Okay. So how do you find x given, sorry, not x given y, x given v? How do you find it? You have to find the joint density of x and v and then divide it by the given one, right? Well, you know the density of fv, this we know, but we do not know the joint density of x and v. That we have to find. Okay. So let's say that v is x plus y, and let's define another dummy variable. We are going to use the transformation method. Let's define another random variable u as x, something which is easy, right? You know, we use a dummy variable. So when you find the inverse functions, you can find it very easy. So x is u and y will be what? Y will be b minus x, but x is u, so y will be b minus u. So you have x and y, the original variables in terms of new variables u and v, right? So let's find the Jacobian. Dabba x, dabba u, dabba y, dabba u, dabba x, dabba v, dabba y, dabba v. Okay, so I'll give the answers. Check this one. And when you cross multiply, the determinant will be 1. Okay, so that will be 1. Now what do you do next? You have to use the inverse of the joint density of, now our x is what, u. So f of u and v, right? Why? Because our x is u. Okay, instead of x, you can write u and v. So what is u and v? That will be in terms of x and y. Instead of x and y, we have to replace it with the inverses of that, u and v, and then multiply it by the Jacobian. Okay, so let's try it. What is the joint density of x and y? Because x and y are independent, right? Joint density of x and y. What is it? F, x, y. Now in this case, they actually p, discrete. So you have to multiply because they are independent. The joint density is the product of the marginals, right? X and y. What will be that? E to the negative theta, theta x, x factorial, e to the negative lambda, lambda y, y factorial, right? Now instead of x and y, you have to replace them with u and v, right? So let's do that. E to the negative theta, x is u, and y is v minus u. So you have e to the negative lambda theta to the power, y becomes v minus u. And then you have to multiply that by the Jacobian is 1, so no change there. So that is our numerator. What we want is the conditional density of x given v. Okay, so this is same as the conditional density of u given v because our x is u, right? Okay, so we have the top, okay. And at the bottom, we have the given density Fv. What is our Fv? V is Poisson theta plus lambda. So that will be e to the negative lambda plus theta to power v divided by v factorial, right? Solving this, the simplifying this will take a lot of time. So you can, some terms will cancel out. But anyway, if you leave it like this, that is also enough, right? So there's no need to simplify it. Leaving it like this will be enough, okay? Right, it's 7:28. So these are some of the questions from 2019 and 15. Shall we do it in the next discussion? I think it will be too much, 2 hours already. Do you have any other questions so far with the examples we did? Okay, so I have a question. Is it possible to ask a question like derive the joint PDF of y1 and yn? Yes. There will be a question like that. I think there is a question that I have selected. That means the joint density of the minimum and the maximum, right? So in that case, you have to use again the transformation techniques. And I'll in the next discussion, I will do a question like that. Okay. Anything else? So I will do another discussion maybe next week. Is that okay? If you are doing the, now there's another question, do we have to find the Jacobian function if the distribution is discrete? If you are using the transformation technique, yes. If you are using the transformation method, you have to find the Jacobian, okay? But if you are using the CDF or any other method, then it is different, okay? But if you are using the transformation techniques, you have to find the Jacobian, yes. Okay, so and in the next discussion class, I will discuss the other selected questions from previous exams and also Tut 4. Okay. So meanwhile, I will upload these questions. You can also try them. Okay. So there are about up to here. The others I was planning to write them and do it. Okay, but you can try the rest of the questions until we do the discussion next time. Okay. So is this helpful to you? Is the discussion helpful? Okay, then so if you think that you have to do extra examples in the second discussion, okay, we'll see. So I'll, so when can you do the next one? Is it okay, 5:30 to 7:30 again next Thursday? Shall we do next Thursday, 5:30, 7:30? Okay, so next Thursday, 5:30, 7:30, we'll meet again to finish the rest of the questions. Okay. So meanwhile, if you have any other questions, please send me an email. So I'll try to incorporate similar examples or that exact example.